So in the last lecture, what we had derived was minimizing influence of the random shock term in its squared form, because the direction is something which should not bother us. So we took summation ui square equal to this, and we wanted a straight line. Therefore we need these two parameters which are unknown. Y and x are known values, and in the presence of those known values, we want to find out a pair of a and b such that summation ui square would be least, hence the name least square equations. And if we take differentiation of, that means we take the derivative of the summation ui square with respect to a, it yields this condition. We do the same with respect to b, it yields this condition. These are the two conditions which need to be fulfilled simultaneously. That means in this we know summation yi, we know summation xi, we know products of y and x. It is this part that we are going to deal with little elaborately in the next part of the lecture. Similarly, summation xi again is known. Please notice that the same term appears here. Summation xi square of course is known because xi are known. So the L is known, that is number of paired observations of y and x are known. So the only unknowns that exist in these two equations are a and b. So given these known quantities, namely summation yi, summation xi, summation yi xi, summation xi square, and n, we want to find out what the values of a and b, and this is something which is simple two simultaneous equations with two unknowns a and b, and we solve for them. When we solve for them, we get following formulas, and like as we do in case of whole simultaneous equation, we solve for a from this and then substitute that value in this equation so as to get the formulas that we had derived last time, which are simple y bar. We get the condition of a, solution for a would be y bar minus beta times x bar. And for b, we get the condition which would be summation yi xi minus n times x y bar x bar divided by summation xi square minus n times x bar square. As you can notice, this is the formula which looks a little different. This is a rather straightforward formula for b. Now if we look at the numerator of this solution that we have got from this simultaneous equation, look at this numerator. This numerator is in fact the easily recognizable kind of quantity that is usually taught in descriptive statistics courses. This is something which we usually call covariance between x and y. You'll notice that in either of these cases, we can also divide both of them by n. And if we do that, we get what is called covariance between x and y. Both things divided by variance of x. This is the expression that we get. So it is a covariance, and this is covariance between y and x, and this is the variance of x. As both numerator and denominator get divided by same quantity n, competition rate doesn't really matter, we can ignore. Important thing to notice from the covariance formula takes us slightly into a different kind of way of looking at it. It's not different, but it is just in its appearance it looks different. Please notice this as follows. We have got y1, y2, y3, etc. to yn. Similarly, we have got x1, x2, x3, xn. Now, the formula that we have derived for covariation, that means not divided by n, which is usually called covariation, which we are going to denote later by s xy. S of xy, please note this is small x and small y. From where does it come? It actually comes from the fact that y bar subtracted from each of these observations. Similarly, xy is subtracted from each of these observations. And what we get are in fact the deviations of these y values from the mean of y. We will call this small y1, small y2, small y3, small yn, anonymously small x1, small x2, small x3, small xn. And what is the formula that we have got for covariation? There is s of xy. S stands for sum. Small x into small y, that means this into this into this, and so on. Because it is in fact nothing but summation of xi minus x bar into yi minus y bar. If we take the product and then operate summation operator, it reduces to the expression that we have got, namely summation xi yi minus n times x bar y. Now let's write this. If we were to write this in the deviation form, because as you can see that this is nothing but small xi, this is nothing but small yi. If we write them in original quantity levels, then we get the expression like this. But this whole thing can be substituted therefore by simply a product of small xi y, summation small xi y. And this is in fact a much easier, better, meaningful way to look at. A, computationally it becomes a lot easier. B, we can now associate the meaning of the relationship between x and y by looking at these quantities. The way I have written this is primarily to emphasize that I can consider this as a vector and this too as a vector. So I have got two deviation vectors from the original data. This is the deviation vector of y, this is the deviation vector of x. And as we see that if we take a product of this, it results into summation xi y. Now let us also simply translate it to the usual multiplication that occurs between any vectors. What is that multiplication? Suppose I write it like this, y1, y2, y3, deviations of y. These are getting multiplied by small x1, small x2, small x3, that is deviations of x. So we can define something what is called a dot product of a vector. So for a while, let's make a diversion into what can be called as element of vector multiplication or vector algebra. Suppose there are two vectors a1, a2, a3, an. To avoid complication, let's call them. Suppose these are two vectors, don't confuse this with this a and this b. If you like, I put it as c and d. For example, I can call it c1, c2, c3, cn, d1, d2, d3, dn. So these are the two vectors. Just as we have got the deviation vector of the y as well as the deviation vector of x. What is the dot product? The definition of dot product is take the products pairwise and sum them. So it will be ci di. C1 into D1 plus C2 into D2 plus C3 into D3 and so on to Cn into Dn. This is. So this will be equal to a dot product, but there is also a alternative definition of dot product, which is an identity. And what is that? That is, in fact, take the norm or a length of C and the norm or a length of D. So, what is the norm of or the length of C? Length of C would be like Pythagorean theorem, C1 square plus C2 square plus C3 square and so on to Cn square. Take all these, sum and take its root. That's the length of or the norm of vector C. The similar manner we can write d1 square plus d2 square plus d3 square and so on to dn square. The length of vector D. And if we take these two lengths, then there is a definitional identity of a dot product. That dot product can be defined in, it is quite similar to what is in linear algebra called either product but not identical. But this is the dot product definition, which says take the product component wise and take the sum of all those component wise products is equal to length of C, that is norm of C, and the length of D. But this is further multiplied by cos of angle between C and D. C and D are the two vectors. So this is C and this is D, and this is the angle between two vectors. So we have to multiply the product of lengths of the respective vectors by the cos theta, that is cos of an angle between C and D. This is our definition. Please try to understand this definition. There is a lot of mathematics, which is beautiful mathematics associated with this. In fact, this is also an example, this is also the formulation which will take you to prove a famous theorem which is called Cauchy-Schwarz inequality. And without going into proving or demonstrating Cauchy-Schwarz inequality, let us stick to this simple formulation that I can define the dot product between two vectors, A, computationally like this, take a product pairwise or the component wise and sum all the component wise pair products. They are always by default equal to norm or length of this vector into norm or length of this vector multiplied by the cos of the angle between these two vectors. What is the implication? As you can see, these vectors that we have defined is generally true. Now the vectors that we are dealing with are in fact the derivation vectors. y1, y2, y3, yn, x1, x2, x3, xn. These are all deviation vectors. Now just imagine what do we do with the deviations while computing the length of these vectors. So the length of y would be y1 square plus y2 square and so on to yn square. So we are going to take the square of deviations and sum it and then take the root. This is precisely what we otherwise called in descriptive statistics as standard deviation of y, not corrected for degrees of freedom. That means not divided by n. Similarly, we are going to talk about the x1 square plus x2 square and so on to xn square and take the root, and that will be in fact the standard deviation of x, and this will be standard deviation of y. So what looks like as a length or the norm otherwise, in our case, in the kind of data and formula that we have got, this is nothing but the product of the lengths. And what are those lengths? The lengths would be standard deviation. And if we look at it as simple sum, it will be deviation wise products taken, that is y1 into x1, y2 into x2 and so on. So this is something which is called covariation, and these are the standard deviation. And if we solve for this, what do we get? We get cos theta. So if I divide both sides by length of C and length of D, what I get is cos theta. And as we know, cos theta is a function that always varies between +1 and -1. If you take up any angle, for example, this is the angle. When this point is here, cos will be equal to 1. We keep on increasing angle, it goes to 90, then cos will be 0. Then we go further, we reach 180, that means pi. So at pi by 2, cos will be 0, At cos theta equal 0, it will be 1. At theta equal 90 degrees, that is pi by 2, it will be 0. We reach here, that is pi, 180 degrees, and that will be -1. So cos theta always varies between this. It is this cos theta which in statistics is in fact called correlation coefficient. So in fact, why correlation coefficient should lie always between -1 and +1? because by default, by definition, it is cos theta. Why it is cos theta? Because it stems from easily understood definition of a dot product. Take the dot product and scale it down by the product of lengths of these two vectors. Resultant would be the cos of an angle between two vectors, and that must lie between +1 and -1. Hence the correlation coefficient lies between +1 and -1. So please remember, this divided by this is same as what we do in statistics as covariation divided by the standard deviation, product of standard deviations. So this is the primary definition. More easier way of looking at it when it comes to the mathematically proving it. It becomes convenient to look at what we call a square. So for example, and that's how mostly Cauchy-Schwarz inequality is stated and proven. I take squares of both sides. So this is something like a variation or the variance uncorrected for uncorrected sum of squares of c or y and x, and this will be cos square theta. And then we again divide. And if we take this, what is the length? The length is, now it is squared, so we can call it to be c into ci di whole thing square divided by summation ci square into summation di square. We take a square root, it becomes something like akin to standard deviation, of course, but for the correction for the degrees of freedom, and this will be equal to cos square theta. It is here the Cauchy-Schwarz inequality enters, because Cauchy-Schwarz inequality says that if we take the string of numbers and define what is there in the numerator could be in fact called, it is the square of sum of products. Let me write this, square of sum of products. And what is it that we have got in the denominator? The denominator I have got, just see that these two terms really get transposed. This can be described as product of sum of squares. And Cauchy-Schwarz inequality says that choose any arbitrary string of real numbers of equal length CI, and if we define these as the entities, these as the quantities, then it can be shown that square of sum of products is always less than product of sum of squares. That's the reason why we get cos square theta ranging between -1 and +1, and therefore the cos square theta will always range between 0 and 1, which shows that numerator always will be smaller than the denominator. So this is the connection that we have with the linear algebra part or the dot product definition part, and that's what is actually operative in statistics, though we don't emphasize this in descriptive statistics courses because not all of the students are usually aware of what matrix algebra or linear algebra or vector algebra, whatever you call it. But please note this, because this will also make you aware of how to make a transition from this usual simultaneous equation representation that we have got for the d squares, how that can be transformed into the matrix notation. So let us switch to matrix notation. So this is the first connectivity of the usual elementary results from the linear algebra with its uses in statistics. Now let us look at the equations that we have got. The equations that we have got are summation yi, summation xi equal, summation xi yi equal to n times a plus b times summation xi, and this will be equal to a times summation xi plus b times summation xi squared. Now as you can see, as we had defined the quantity summation xi squared, that is small summation xi squared. Small summation xi squared, it's same thing as summation of xi minus x bar squared, because these are nothing but small xi's, and we square them, and that's the variance, or that is something like the basis of computing. Take the square root, you get quantity similar to standard deviation. Now let us write these equations in the matrix form. So what is the vector that we have got here? This is in fact the two equations in two unknowns A and B, and these are the known quantities. So this is something which is, now I'm going to write this conventional notation of writing simultaneous equation with column of constants on the right hand side. So I will write this like this. And now what are the unknowns? A and B are the unknowns, so I can write them as the coefficients of A and B. Coefficients of A and B would be equal to n in the first equation for A, summation xi for B, again summation xi for B, and summation xi square for A and B. This whole thing will be equal to summation yi and summation yi xi. Simultaneous equation from the same data, but now written in matrix notation, and this will allow you to visualize and also generalize how the same set of equations with the same kinds of patterns that exist in this are something which are more easily compactly written in matrix form when we generalize this not only to y being dependent only on x, but also on x1, x2, x3. That means what we call multiple regression or multivariate regression. So this is a convenient way of looking at it, and as it happens in matrix terminology, if I call this matrix to be some matrix, this is a matrix of constant coefficients for the equations, so how do I solve for it? Solution for A and B would mean multiply, that is, pre-multiply both sides by this. That means the inverse of this. If I produce the inverse of this, and if such inverse exists, then it would be that inverse of this matrix into this matrix, which will be 1, 0, 0, 1. That will be solution for A and B. And this will be, on the other side, you will get inverse of this matrix into this matrix. Of course, while multiplying, you have to be cautious of the size of matrices for the compatibility or the definability for the matrix multiplication. So this is always going to be a square matrix. Later, when we generalize this into multivariate case, this is what we find it. Please note, we can have some properties which can be easily guessed from this. You can get summation xi for the negative, but you cannot get n to be negative, you cannot get summation xi square to be negative. That means you have got a matrix which has got same entries, and has got all positive entries on this. This itself is going to be a very useful kind of an observation to make. We can now just, because we want to write it in matrix form, we can also represent the original data that we had written, which would be compatible with this matrix form. So what is the matrix? y1, y2, yn, and I want something like summation of yi xi. How will I get summation of yi xi? One way of getting that is, I can multiply this by x1, x2, etc. Naturally, you will get the product summation yi xi, but that will give us only one component of this vector. What will give us the next component? And for that, the relevant matrix that you must have needs to be modified. What is that? Suppose if this is the size which has got one row, n columns, and this has got n columns, n rows, one column. So this is definable, and the resultant is one quantity, 1 by 1, that is this quantity. But I don't want this quantity alone. I want this quantity as well. That means what is the size of this matrix? It has got 2 rows, 1 column. So in order to get that, I can make a trick. What is that trick? The trick is, I will write a matrix or an additional vector of the same size of x1, x2, x3, xn. And now you define this. So if y is the original vector, I will get y into x. For example, this row into this column into this row will give me summation yi. This column into this row will give me summation yi xi. In order to make it comfortable and consistent for all later generalizations, we can define it other way around either. I can, for example, take the transpose of this matrix, which will be 1, 1, 1, and x1, x2, xn, and then multiply it this way, y1, y2, y. If I do this, let me call this matrix to be x, then this will be x transpose. Because originally when we write the equations will look like y1 equal to 1 x1, 1 x2. Why is it 1 here? Because actually there is a vector to which we are getting multiplied, that is a and t. So if I define a multiplication like this, now this is more akin to like, now you will see that what is y1? y1 is equal to a plus b times x1. What is y2? a times b times x2, and so on. So this is our original equation. Therefore, if I am going to write it in this manner, then I have to write this as a y transpose, or either I have to write as an x transpose. So what is something which is more conveniently followed is I take x transpose y. So if it is x transpose y, I can write this to be same thing as x transpose y. And what is this? This matrix, or matrix of coefficient, is in fact going to be, and now you can see, I write x transpose. Now you define the multiplication again. 1 into 1 plus 1 into 1 n times, that gives me n. Then I multiply this with this, then 1 times x1 plus 1 times x2, which is nothing but summation xi. So I finished with multiplying with this column to these two rows, and let's move to the next, and I get again x1 into 1 plus x2 into 1 and so on, which is again summation xi. And then the next element would be x1 into x1 plus x2 into x2 plus x3 into x3 and so on. That means I get summation xi squared. So this matrix I can always write as x transpose x. And this is a column of unknowns a and b, which is often usually noted as beta. This is x transpose y. So the same set of equations, when translated in matrix notation, I am presuming that at least some of you are familiar with the matrix notation, one can write that the equation system of the OLS type that we have derived with this condition of minimizing summation ui square looks like the following: x transpose x times beta equal to x transpose y. And now I multiply both sides by x transpose x inverse into x transpose x into beta equal to x transpose x inverse into x transpose y. This yields identity matrix, and identity matrix into beta will be equal to beta. Therefore, the solution will be x transpose x inverse into x transpose y. So there is a point in, there is some advantage in looking at it as a matrix, because later generalization becomes easier, it becomes compact in notation. And more importantly, the nature of coefficient matrix that we get to derive the values and the constant coefficients that we get from the equation system entirely consist of x, but they have certain kind of property. What is that property? The property is that this kind of a matrix, which is x transpose x, has certain peculiarities. When we deal with the multivariate generalization, it becomes relatively easier. But as you can notice from here, as I have told you, it is possible to get summation xy equal to negative, but you can't have n negative. You cannot have summation xi negative. So this is a matrix which is symmetric in nature and which has got all its diagonal elements to be positive. That gives certain kind of an advantage, because it has certain kind of properties. We'll return to that when we talk about matrix in the multivariate constant later, more elaborately later. But this is the formulation in matrix term. So there are two elements that connect matrix algebra with the usual descriptive statistics that you learn with. You can probably learn how to fit a line from the given data, straight line. You can look at it as a simultaneous equation, but if you look at it as a matrix, there are certain more additional insight that you can get. More notably, if you define the deviation products of y and x as two vectors, and then we can, that being a product which is of dot product type, then it generates a statistically important quantity called correlation coefficient, which is, mathematically speaking, in terms of vector algebra, it is nothing but the angle between two vectors. Therefore, the coefficient of correlation must lie between -1 and +1. So, this is one part that we are going to deal with. Now we are going to look at this very connection that we have got with the correlation coefficient using somewhat different notation, and it is more easy to see by changing this notation. I am going to denote sum of deviation products S of xy, which is nothing but this quantity yi minus y1 into xi minus x1. And I am going to denote similarly sum of S stands for sum, deviation is small x, 2 small x means square, it is sum of squares of deviations of x, which is going to stand for summation of xi squared minus x bar squared. You expand this and then you get a quantity which is in fact summation xi squared minus n times x bar squared. Analogously, in this case you get summation xi y minus n times x bar y. Usually in statistics you are told to divide these quantities by n. If you divide this by n, we call it covariance, whereas this will be called covariation because it is not corrected for degrees of freedom, that means it is not divided by n. Similarly, this will be called variation of x. Doesn't really matter because, as you know, in many cases we divide both numerator as well as denominator by the number of observations that is n. So in a way, dividing by n is redundant. Only advantage with the covariance and variance is, now notice this again, similar kind of a transposition of term that occurs. If we divide it by n, you get 1 over n into summation xi yi. And then this n will disappear, and what we get is x bar y. So when you define covariance, what is the description? The description is, this is nothing but, because we are dividing it by n, we can call this to be mean of products. Whereas this is something that we can define as product of means. Same here, if we take variation of x and divide it by n, we are going to get 1 over n into summation xi square. Again, we divide this by n will get cancelled. What remains is x bar square. So again, we can define this like a similar simple transposition of the terms. We can call this to be the mean of squares of x minus square of mean of x. So we are just transposing this term mean and square, and we get this, so it is easier to remember. That's one of the advantages of defining it as covariance and variance and covariance rather than variation and covariation. But still, this is again related to the same idea that is there in Cauchy-Schwarz inequality. Okay, so I'm going to stick to this notation. If I write the same thing in deviation form, which we are going to use later in order to prove certain other claims concerning OLS, this can also be written as small xi small yi, because this is small y, this is small xi. So I can write it this way. Similarly, this expression, instead of writing it as summation xi square minus n times x bar square, I can also write this as some small xi square, that is squares of the deviations added up. So we are going to change these notations and interchangeably keep on using these notations because they can become a little more handy and we have a less messy algebra. So this is something which you can easily note. And later we are going to switch this notation. Instead of using s of x1, I will find it convenient. You will find it convenient to understand it as like this, and this also in form of s square. So later, for example, by proving the linearity property, we will be using this notation. Okay, but for a while, we are trying to explore in what sense the definition of B that we have got, this definition of B means what? We are trying to define B to be fitted with this to this given data of y and x such that the deviations from the values of line defined by A and B when squared and summed would be minimum. And what is that formula? The formula again alternatively would be equal to, in this notation it will be equal to S of xy divided by S of xx. Alternatively I can also define this as summation xi yi into summation xi square. Same thing but alternative notation. Okay. Now let's see what it really means. So having defined these quantities, let us now look at what do we really get as minimized summation ui square. That means if I am going to write, for example, my way of estimating A is going to be y bar minus b times x bar, b equal to S of xy divided by S of xx. Now what if we are going to substitute these expressions in the expansion that we get? This is the next step, and this is a little more elaborate algebra that we will continue in the next lecture. So that we will be able to see the connection of the coefficient that we defined as the slope coefficient is nothing but the kind of a transformed version of the correlation coefficient between y and x defined by this quantity. This is a quantity which can be negative. This is a quantity which has to be by default the positive one. But correlation coefficient can be negative. So if it is negative, it is S of xy which is going to be negative, not of S of xx. So there is a definitive connection that connects the OLS estimate with what we simply define in descriptive statistics as the correlation coefficient. In fact, it is nothing but a version of, that is modified version of correlation coefficient. So I give it to you as a problem. Just try to see in what sense we can write B in terms of the known statistics. What is known statistics? These are all known statistics. For example, if I take the root of this, S of xx, or root of y, S of yy, which will also be again analogous to this. Sum of squares of deviations would be equal to simply summation y square minus n times y bar square, or alternatively it will be summation y square. So just think of this, because with all this great differentiation exercise that we made, there are certain properties which emerge. One of the property which can be again noticed from these formulas themselves is, as you can see, that A is defined using the slope coefficient derived from this formula, but it contains additional data, that is y bar and x bar, which really means that the line fitted by OLS is going to necessarily pass through a paired observation called y bar and x bar. And this is also a very important property because it ensures that something concerning the error term. What is that? That is another question that you should try to probe, which we'll be dealing with in the next lecture. What is the significance of line necessarily passing through? That means we have got these data points, and there is some line which we are going to pass through, and this line must pass through this observation through a point which is called x bar and y bar. So it must contain x bar and y bar. So we are going to look at two ways which are rather familiar from descriptive statistics. One is to understand that line passes through x bar and y bar. What is the significance of that with respect to the nature of error term, or rather the nature of error term in terms of its mean. And secondly, we are going to relate the slope coefficient formula that we have got, which is covariation of x and y divided by variation of x, how it is related with a related formula which involves the same quantity in computation of correlation coefficients. So that's our next step, which we'll be doing primarily by using this kind of a notation because it becomes relatively easy and transparent